Section 2 of Chapter 13 is called Simplifying Polynomials, which is basically going to be a whole bunch of combining like terms. So the key thing to remember is that terms are like terms when they have the same variables that are raised to the same powers. A and a squared are not like terms. Keep that in mind as we go. So, first example here, we have 3a plus 2a squared minus 3 plus 6a minus 4a squared. As a general rule, we try to work from the biggest exponent down. So the biggest exponent in this problem is 2, and that is on this plus 2a squared and this minus 4a squared. So those are like terms. I can combine them. I have positive 2 of them early in the problem, and at the end of the problem I have minus 4 of them. That means grand total I have negative 2 of them. I have negative 2 a squareds. Okay, that's because I have positive 2 and minus 4 later. Let's move down from a squareds to just a's. We have a 3a at the beginning of the problem and a positive 6a later in the problem. 3a plus 6a is positive 9a. And then as far as things that don't even have a go, there's just this minus 3 hanging out in the middle of the problem, and he's now going to live on the end. Okay. A couple things I want to point out here. First is that you must realize that the sign for the term comes before it. Okay. This was an issue for some of you in chapter 10. This is why when I'm highlighting my terms, I'm including the sign before them when I do so. I want you to see exactly what the term is. It's the sign and the number set. Second thing is this answer is in what is called descending order. Okay, descending order just means we have the highest exponents first, and we work our way down to things that don't have exponents, and then down to numbers by themselves. Do you absolutely have to do this year? Not necessarily. It's an excellent habit to get into, though. There will be a time later in this chapter where I'm going to require it of you, and speaking from experience here, you're going to do a whole lot of work with exponents in second half of Algebra 1, and then in Algebra 2 and on, there's just exponents everywhere. You want to get used to using descending order because it's neater, and it's how almost all of your textbooks will always handle exponents. So it's just a good habit to get into now. So moving on. The next thing we have negative 3x to the fourth y squared plus 10x to the fourth y squared minus 3x squared minus 5x to the fourth y squared. So here there are 3 terms that have this x to the fourth y squared piece to them. And they're the first, second, and fourth terms. Those are all like terms because their variable portion are identical. X to the fourth y squared, x to the fourth y squared, x to the fourth y squared. So we can combine those into a single term that has x to the fourth y squared. There's no need to write that 3 times. So we start with negative 3 of them at the beginning of the problem. We then add 10. Negative 3 plus 10 sets us up at positive 7. And then at the end, we take away 5 more. So if we have 7 of something and we take away 5, we're left with 2 of that thing. So we have 2 of that thing. That thing just happens to be x to the fourth y squared. And again, we did that first because x to the fourth y squared have big exponents. They have a degree of 6 in total. And that's much bigger than the degree of 2 on this leftover term by itself. Which, by the way, we can't forget that leftover term. He has to come along to be part of the answer, negative 3x squared. Okay. So this next guy, 4m squared minus 2mn plus 3m. So the biggest exponent here is 2. But there are no other m squareds to combine that with. Okay, that's fine. mn, in theory, also has an exponent or a degree of 2. But there are no other mn's to combine it with. And 3m is, again, great, but there's nothing else to combine it with. This is already simplified. There's nothing else we can do to it. I'd like to point out this is in descending order. Okay, anytime we have an exponent squared, a pair of variable squared, pair of variables, single variable, that's the order we'll put them in. The single variable squared goes first, the paired letters go second, and the single letter goes third. Okay, so now we can move on. Nothing we can do to that. So this next guy has a whole lot of stuff. There's x to the fourths, there's x squareds, there's an 8 that doesn't even have an x. So the biggest thing there was x to the fourth. The highest exponent was x to the fourth. So the first thing I'm going to do is find those, mark them off, and they're both positive. So that means there are truly 8 x to the fourths here. And then I'm going to go through and I'm going to mark off my x squared terms. So there's one there, there's one here, and there's one here at the end. So there's 3 of these to put together. The first one is just a single x squared. When we add that to 9x squared, we have 10 x squareds. And then we take away 6. So 10 take away 6 is positive 4 x squareds. And then there's this negative 8 that doesn't have anything else to combine with. So he just comes along and gets tacked onto the end. Okay, next guy. Negative 4a squared b plus 10ab squared minus 3a squared b minus ab squared plus 2ab. Lots of a's, lots of b's, exponents of 2 floating around. So the highest degree of any of these terms is 3. The a squared b terms have a degree of 3, and the ab squared terms have a degree of 3. So let's talk about which one we want to look at first. So we're talking about descending order. I'm trying to get you guys used to this idea of descending order. When we have something like a squared b and ab squared, the first term, since they have the same degree, that we want to focus on is going to be the a squared b. We want to work from the earliest alphabetical square, if that makes any sense. A comes before b. So since I have problems where a is squared and b is squared, I want to look at the a squareds first. Also, I hope we realize that a squared b and ab squared are not like terms, because the square moves, and that can't be with like terms. Like terms have identical variable portions, and a squared b and ab squared are not identical. So I'm going to do all my highlighting first this time. So I start with my a squared b pieces. In a different color, I'll mark off my ab squared pieces. And in that sad blue color that always only seems to have one person, we'll mark off the guy that doesn't have exponents at all. So now it's just a matter of putting together the things that can be put together. We have negative 4 and negative 3 a squared b's. So when I combine those, that's negative 7 a squared b's. I have positive 10 and negative 1 ab squareds. So that is a positive 9 ab squared. And then, of course, we cannot leave the 2ab off the end. Last pieces here are distribution, to remember how to do it. So this problem here is just a straight up review of how to distribute. Give the 5 to both terms. It's multiplication, so you'll multiply it to the number part only. 5 times 2x squared is 10x squared. And 5 times 6x is 30x. If there's distribution to be done in a problem, it must be done first. You cannot solve or simplify things when one is in parentheses and one is not. So that's this next problem. You can see the two things that have ab squared, but the problem is one of them is currently in a force field of parentheses. To get rid of the parentheses, we must distribute this 2 outside of it. So 2 times 3 is 6 ab squareds minus 2 times 6 is 12b. And for the moment, the rest of this just gets brought along. So plus 2ab squared plus 5. And now my terms, we have the 6ab squared out here, the positive 2ab squared there, and then the negative 12b doesn't have any other b's to combine with, and the positive 5 out here doesn't have anything to combine with either. So they are separate terms. So just combine the two yellow boxes here. That's going to be 8ab squared, and then bring along the other two terms that have nothing to combine with.